Okay, so welcome everyone to the Paper Club. Today it's Caio's turn with theory-guided data science. He's prepared a presentation for us. And Caio, if you can take it from here.
All right. Thank you, Victor. Hi, everyone. My name is Caio Damasceno, and today I will be presenting this paper called Theory-Guided Data Science, a New Paradigm for Scientific Discovery from Data. Well, to begin with, I would like to present the plan I have for the presentation, the summary, so you can have a general idea before I start talking of each topic individually. I will begin with an introduction on the topic, the motivation of the paper, and then I'll proceed to those 3 sessions where we discuss the implementation of this paradigm in different steps of modeling. First, on the design, that is the previous part before running it, then the model learning, when the model actually does stuff, and then the output refinement, when we treat with theory guidance the output of the model, the final part. Then I'll proceed to hybrid models of theory and data science, how they can one help each other and complete each other. And finally, the theory augmentation using data science, like using data science to increase the power of theory. And then I will wrap it up with a conclusion to understand, in general terms, everything we have seen. Well, first things first, the introduction. When we speak of data science with theory guidance, we have to remember what we understand for scientific method. And doing a brief summary of what scientific method stands for, we have to remember that it begins with an observation of something, of a phenomenon, and then a question. This observation gives rise to a question. And these questions leads to a hypothesis of why this happens. Then we test the hypothesis with experiments, and then we analyze the results of the experiment, and it leads us to a conclusion. And with this conclusion, we can establish a thesis, a bigger understanding of the phenomenon we have observed at first. And what's the point of comparing the scientific method with the applications of data science? Because some people might say that data science could be the end of theory. Why would data science be the end of theory? Because data science sometimes presents itself as a black box application. That is, we use the experimentation, we use our results of like phenomena of nature, of things we observe, and we extract conclusions of it through the analysis without it leading to a bigger understanding of the phenomenon itself. We make prediction, but sometimes we skip the inference. We don't infer anything because it's a black box application. So something might lack on the scientific method depending on how we use data science applications. And those black box applications, although they are very powerful and lead to big results in the scientific domain, it has 2 main problems that cause limited success of those applications in scientific domains. The first one is the paucity of data. What is that? Sometimes we have data samples or we have measurements that don't represent the true nature of the relationships we are trying to observe. Sometimes we are trying to understand phenomena that are too rare, and our data is not enough for us to provide to a model, and it understands this phenomenon because it's underrepresented in our data. So sometimes we don't have enough data to trust black box applications alone. The second thing is the interpretability, because the analysis leading to a bigger understanding of cause-effect mechanisms is a fundamental part of science. So with science, we want to understand stuff. So if we make predictions without understanding, we are losing something. So this is also one big concern when we talk about using data science in the scientific domains. And what is the goal of the paper? The paper aims to build the foundations of theory-guided data science. And let's understand how this theory guidance works. Here I present a graph that shows the difference of theory-based models and data science models when we compare the use of scientific knowledge and the use of data. When we talk about theory-based models, we don't need, we can, but we don't need to trust data so much at first. We can have a small sample of data and do theory with small data. And what are the advantages of theory-based models? They're good for well-understood processes. That is, I understand this, and then I study this with my understanding. They work very well. They have a big use of scientific knowledge. And what are the disadvantages? The disadvantages are when I don't have a good understanding of the processes, I have to make simplifying assumptions. And if I make simplifying assumptions, it might be bad for my approach. It might compromise my results. When we talk about data science models, we can rely only on the information contained in the data. Like I can't start from no knowledge at all and still get predictions, get conclusions. So I don't need to start with a high amount of scientific knowledge. What are the disadvantages? I may capture associative relationships of poor data. That is, if my data is not rich enough, when I talk about the phenomenon I want to observe, I will capture those spurious contributions, those contaminations in the association of my data, and it will lead to bad conclusions. So here we are talking of two extremes. And what is the idea of this paper? On their words, it's a novel paradigm that uses the unique capability of data science models to automatically learn patterns and models from large data without ignoring the treasure of accumulated scientific knowledge. So we use the power of data science, but we also use the power of knowledge. And then we reach better results, and we do science the right way using data science and trusting the power of those tools. So to continue, the first approach I will talk about is theory-guided model design. That is, on the first part of my study, I have to think of my model design and how can theory guidance help on this. Well, the first possibility that the paper presents is theory-guided specification of response. What is that? It's to use combinations of response and loss functions that are consistent with what we know. I know stuff, so I make choices of response and loss functions that make sense and correspond to the prior understanding that I have of the process. One example here. When modeling occurrences of unusually severe floods, that is extreme events, using a Gaussian response might not be adequate. So maybe a Gumbel distribution will be more accurate and meaningful because the Gumbel has this long tail. So if I'm talking about extreme results, and if I want to make sure my model handles well extreme results, maybe I have to think of a response distribution that includes this domain knowledge that I have. And this is one of the possibilities that the paper presents. Think of the previous knowledge when you think of response and loss functions. Well, the second possibility is theory-guided design of model architecture. That is, use scientific knowledge to influence the architecture of data science models. What is the example that the paper gives? For example, if you want to describe overall surface water discharge, That is, if you want to understand the discharge of water surfaces as a process, it might work well if you have knowledge of the sub-processes that lead to water discharge. You learn models for each sub-process separately. So I am architecturing my model, and then I separate on steps that I know well, that I have knowledge. I might not have knowledge of surface water discharge well established explicitly. I might not know this, but if I know how rainfall and evaporation works, if I have a good theoretical knowledge of this, and surface water runoff and groundwater seepage, I might do this this model in steps using the knowledge I have of each step, instead of doing a black box model of the final result that I want. So I break into small steps that I know. And this is the other approach that they propose for model design. For theory-guided model learning, that is, on the central part of modeling, after I design my model, I do the learning. And what are the proposals that the paper make for this part of analysis? The first one is theory-guided initialization. That is, use domain knowledge to provide educated initial values to the model. In one example, maybe you don't have enough data for a pre-training strategy, but if you have theoretical knowledge of a process that can be used as a pre-training, you can run computational simulations of this using the theoretical knowledge you have, and then use the results of this model that uses computational simulations to initialize your model. So you want to understand the process, and you know another one, but don't have data about this one. Run computational simulations of this previous model to use as a pre-training strategy. Another one, theory-guided probabilistic models, and they propose two ways of doing this. One of those is the automated graph estimation. That is, to use domain knowledge to explore graph estimation techniques, limiting the search to physically consistent solutions. That is, I limit the search for my estimation to things that make sense with the knowledge I have, that are allowed by theory. So I don't waste time and computational power doing things that are not allowed in nature or are not allowed in my theory. The second one is introducing priors. That is, use scientific equations and domain knowledge to guide theoretically priors. And a very interesting example is the use of it in electrical activity in the heart. There are studies that have to predict electrical activity in the heart in 2,000 locations. But like, you can't place 2,000 electrodes in the heart. What you do is to place 100 electrodes in the torso of the person. So you can use electrophysiological equations to help determine the spatial distribution of those electric signals. And what those equations, those known equations do, they understand the electrical signals in the heart at time t based on the predicted signals at time t minus 1. So you use data of the previous time to help the lack of possibilities you have using theory. So you have a limitational, practical limitation here, and then you use data based on your theory. Another one is theory-guided constrained optimization. What is it? It's the use of theory-guided constraints to restrict the space of model parameters. And this example is important, and we will go back to it in a few minutes. And what is the example they give? You can use satellite images to help identify water and land areas. But like the quality of images, of satellite images for doing this might not be that good. So what you can do, you can use elevation information to improve this, because water fills lower areas first. So if the area is higher, the probability of it being covered by water is lower, because it fills the lower places before reaching the higher places. So you can use this as theory guidance for optimization. And here is an example. You have here as a plot of this data using two features, and the circles are land areas and squares are water areas. And here, the darker the color of the point, higher the elevation of this point. And if you use a traditional boundary, a model not using those theory guidance, you see that we separate in two groups, where places with low elevation are on the same side as places with high elevation. But if we introduce this information that higher places tend to be less filled with water, here we have another boundary where it makes sense that average locations of average elevation are on the same group that higher elevation, and not the opposite. So here the model was clearly improved by this use of theoretical knowledge of the difference that water coverage has depending on the elevation information. And the fourth example for guidance in model learning is theory-guided regularization. Regularization techniques might be science agnostic, and using group lasso as an alternative, you can assume that features can be grouped together. So the feature importance that will be determined for each group. So if one feature has a low parameter, it means that all of those features that are in this group will also have. So you do regularization in groups of features. Like, for example, genetic information that is closely located travels together between generations of population. So if you want to make a genetical heritage study, it makes sense to group this genetic information by their proximity. And like it can have plenty of applications on our cases as well, thinking of grouping by MCC or other properties of merchants. And it might be very good for grouping together features or grouping together our data depending on similarities and those things. Well, so the fourth part in the final step of the process of learning is the output refinement. And the first example they give is the use of explicit domain knowledge. That is, you have a domain knowledge and use it at the final stage of the model to refine plausible outputs. And that is pretty straightforward. You have a knowledge, you know what results are not allowed theoretically, and you filter them. And for example, in material discovery, you might want to find materials that have specific properties. And like you could run over plenty of possible combinations of materials and try to find those that have those properties. But probabilistic graphical models can efficiently predict a material's structure and properties. So you can use those models to filter the possibilities and find more easily the materials you want to find for specific characteristics. So you narrow down the search depending on the desired features. A second example would be using implicit domain knowledge. That is the same as the example before, but now you don't have the knowledge in the form of explicit equations. You have a knowledge in another way. And how is this? How does it work? For example, when going again to the mapping of water and land areas, we saw that elevation data can enhance the accuracy of the classifications, but it's not so easy to have this data. Like you have to make measurements of elevation across the globe in many areas, in many lakes or rivers or water places and non-water places. So it might be hard to use this data. And if this data is not available, a location that has been identified as water many times has a higher probability of actually being in a lower place. So if there is water in this place frequently, and in the other place next to it, there is not, that means that in this place where there is usually no water, it's probably higher. And the one that has water more frequently is lower. So you can use this to iterate on your prediction and feed your prediction with those previous measurements and reach a better response. Then now we have covered the previous, the during, and the final steps of learning. And now we will enter two other approaches for theory guidance in data science. And the first of them is hybrid models of theory and data science. That is mixing together both. How does it work? We create hybrid combinations where some aspects of the problem are handled by theory, and the remaining components are modeled using data science components. That is, when one of them fails, the other one takes count of the problem. And the first example is theory being input in data science models. I use my theoretical knowledge as input in my data science model. How does it work? I have data, I have my inputs, and I have my theory. And with my theory, I can have a YTO, that is a prediction, a theoretical prediction using the theory that I have. But I want to run a model. And I can run a model with my inputs and reach a prediction, and it might be very different from my theory. But my theory might be well established. It might be a good guidance for my results. So what can I do? I can use the theoretical prediction also as inputs in my model. So I can guide my prediction. I can use my theoretical predictions to train my results of my model. So I reach results that make more sense theoretically. It can learn from the theory using theory as input. The other example is the opposite, using data science as input in theoretical approaches. I have a theoretical approach that lacks some understanding, that has limitations, and I want to use data science to complete my understanding. What is a good example? In aerospace engineering, turbulent flow might be very complex and heavy to computate. And we can model this turbulent component through the stress variable. But the models we have, the theoretical models we have, don't return a very good results compared to experiments. The theory lacks something. So what is done? The Navier-Stokes models are too complex for specific problems. So Ryan Reynolds, no, a Reynolds average Navier strokes model can approximate the Navier stroke model, but it doesn't reach a good result comparing to experiments. What can we do? We can use a computational component, a discrepancy component using a random forest model to take account of this difference. So we have a component handled by the theoretical approach and a component handled by the machine learning approach. So we can reach a better result on understanding turbulent flows. And finally, the theory augmentation using data science. They give two examples in the paper. The first one is data assimilation in theory-based models. What is that? When you have dynamical systems, maybe just using your features might not be enough for good predictions, because you have to constrain the results based on the previous values. For example, if I know that 1 hour ago the temperature was, I don't know, 23 degrees, 1 hour later the temperature might not be that far from 23. So you can use data in theory-based models to feed your prediction with values that actually make sense, and augmentate the theory using those data information. The second example is calibrating theory-based models using data. That is, I have a theory, but I don't know the values of the parameters, so I can use data science to optimize those parameters of my theoretical model without having to search over all possible values. I can find ways to optimize my search of my theory, and I use data science to reach a better understanding. That is the problem we're trying to tackle. I use data science to improve my theoretical understanding, finding optimal parameters. Well, going to our conclusion. First, the paper provides a non-exhaustive conceptualization of theory-guided data science. That is, it presents many approaches, many alternatives, but like there can be many other ways of doing this. It's non-exhaustive. And it seeks to use the power of data science, but without ignoring the treasure of knowledge accumulated in scientific principles. We can use the best of both of the worlds. The central motivations are anchoring data science algorithms with scientific guidance, that is, doing things with data science that makes sense with our understanding, and advance the knowledge, like the motivation here is not reaching good predictions alone, but also increasing our understanding of the problems, and all of those examples work in this direction, and ensure interpretability, help us make inferences using our data, and ensuring we can interpret the results that we get. And finally, while most of the discussion is focused on supervised learning, those research teams can be explored for other types of tasks as well. But like this is more presented like a first step of introducing this paradigm, establishing this paradigm, but the possibilities are almost unlimited. You can think for yourself of applications of the things we see here, and I wanted to bring this because although here we might not be interested in general in understanding of phenomena of the nature, we have knowledge of the things we do, we have domain knowledge, and we can use it in our favor when we are trying to model stuff. So we can think of applications of those approaches. We can think of similar approaches motivated by what we see in this paper, and use this in our advantage, trying to improve our analysis. And that's it. Thank you very much.
Thank you very much, Caio. Great presentation. I think now would be the moment to open up to questions or discussion. So if anyone has a question, feel free to start or let me know and I will. All right. So I think I'll start. I was thinking about especially in the beginning when you're talking about the theories. First, I think it's like really interesting, but how does one balance bias, right? So I was thinking about one of the more interesting applications of this theory interface with data science would be in discovering new theories, right, within how the data and the weights are organized. So, for example, understanding how the brain processes language based on how a neural network processes text, for example. How do you balance bias in that sense? How do you balance keeping yourself open to new possibilities while trying to stick to established methods? You know what I mean?
Yeah, I think so. I think we have to be balanced in this guidance of theory, because a theory might be right now, but experiment might prove that it's wrong a few times from now. So if we focus on guiding our analysis on theory blindly, we might be perpetuating some things that could be improved. So, like, I think what the paper encourages us to do is like to use one to feed the other when we talk about theory and data science. Like, don't trust theory alone, don't trust data science alone, but use data science maybe in this question, if I could understand what you meant, is to use data science to like improve the theory and try to find ways of getting more accurate results and find different approaches, theoretical approaches. So not only like use theory as sacred when doing data science, but also trust data. If we have good data and it's not compatible with theory, the theory might be wrong. So I think the short answer would be have an open heart and don't think that theory is unbeatable. No, like if it does not correspond to data, it might be wrong.
Yeah, I think that was pretty much what I was asking. Thank you.
I have more of a personal question. I'm curious how you found this paper and what made you choose this paper.
Well, I come from a scientific field, right? I worked with physics before joining you guys here at CloudWalk, and I have, when I was having my first contacts with data science, I had this concern on how we could like this question here. Sorry, this is data science the end of theory? That was something that I came across some time ago, and I was thinking like, is it good enough to have results and make predictions, not understanding how we get those predictions? Like we have good performance predicting how nature works, but we don't understand it, like black box applications. And I think it's just one of the goals of science. Science indeed wants to make predictions, but if we don't understand what we're doing, how we reach those predictions, we're losing something in the scientific method, in the scientific discovery. So that was something that I have been thinking a little bit, and when I was trying to find something to use here, and sometimes I come across those type of problems in the things I do. Like I'm working on a model of churn, and recently we've been talking like, okay, we can reach one day a good model to predict churn and find out which merchants will churn, like even before they stop transacting, they're still transactioning, and we know that they will churn. It will be like the best of the worlds. And but if we don't understand what is leading the merchants to churn, something is missing. We have to understand what leads to churn so we can work on it and avoid churn. For what does churn prediction serves if I can't stop it, if I just have to run after the ones that left us and not work on manners of avoiding this to happen? So it's something that I think about sometimes, the importance of interpretability of what we do. And when I was thinking about what to present, Mateus gave me the idea to find an interface of my previous experience in scientific, in the scientific area, and what we do here. So I thought this would be interesting, and like doing some research with some keywords, I found this. It has this paper. It has a lot of citations, so it caught me, and I got curious, and I thought that it would be interesting for us to discuss.